So if we can find the derivative, we know that we can find the slope. The question is, what are we going to do with that? Well, to see what the slope is good for, let's think about a case that you probably are pretty familiar with. Suppose that you're manufacturing something and it costs you $1.75 per item, plus you have fixed costs of maybe $30. This is just like it costs you $30 to make the payment on your factory, and then $1.75 in labor and materials for each item that you make. Okay, so we have this linear equation. Of course, the slope is $1.75. Now, when you know the slope, that's pretty handy because you know if I make an extra item, then the slope says for every one I go over, I go up by 1.75. So, in other words, the rise over the run is the slope, right? So the change in y over the change in x is the slope. Or another way of saying that, the change in the output, the change in y, is going to be the slope times the change in input. So if I change the input by 1, if I make one extra item, then the change in my cost is going to be the slope, which in this case is $1.75 times 1, so my cost is going to go up by $1.75. Well, that's pretty simple, right? So, but what if I make an extra 10 items? So we're talking about increasing the quantity by 10, then how much will the cost go up? Well, $1.75 times 10 is $17.50. Okay, so if you know the slope, not only do you know the rate at which things are changing, you know how to figure out how the output will change when you make a change in the input. That's pretty useful. That's the idea of a differential. Now, with a nonlinear function, let's say y is some function of x, but it's not linear, so we can't read off the slope. We can still find the instantaneous slope. Right? We can find dy dx, or sometimes it's called y prime. Right? That would just be the derivative. Right? And in an infinitesimal sense, we're talking about a teensy tiny change in x over divided into a teensy tiny change in y. So in an infinitesimal sense, the change in y, teensy tiny change in y, is f prime of x dx. Now, if these aren't super tiny changes, this is still approximately true. The change in y is roughly the slope of the function times the change in x. Okay, so we want to look at an example here where we've got a function. Y is this nonlinear function. Right? It's x cubed minus 2x, so we can't quite read off the slope, although it's not hard to find the slope. We're told x is about 5, and we're anticipating making a change in x, which is going to mean there's going to be a change in y. So how are we going to get the change in y knowing the change in x? Well, we know the slope, dy dx, is 3x squared minus 2, just from our simple derivative rules, right? So we know that if you take that slope times a change in x, an infinitely tiny change in x, that will give you the proportional change in y with that, right? And we know that even if the change isn't super tiny, if it's not too large, this will be approximately true. So that's what we're going to do. What we need, though, is to figure out what actual value of the slope are we talking about. If we look at our derivative, dy dx, and we evaluate it at 5, remember we're told that x is about 5, then we can get the approximate value of the slope. We plug in 5 here. 5 squared is 25. 3 times 25 is 75. 75 take away 2 is 73. So the slope is approximately 73. So that tells us that the change in y is going to be roughly the slope, which we're near 5, so the slope is about 73. The slope times the change in input. The change in input is 0.03. So let's see. So we can just quickly multiply these. 3 times 70 would be 210 plus another 9 makes 219. So we just have to move the decimal place to the right, so we get about a change of 2.19. That was pretty quick. Knowing the slope, it was about 73. Knowing the change in the input, we can figure out the change in output. Just multiply the slope times the change in input. And this expression here is called the differential. So it tells us in an infinitesimal sense how does y change with x. And basically, the change in y is the slope times the change in x. Now, since this function is nonlinear, the slope is always changing, right? But we can say, all right, even though the slope is changing so that the graph will curve away from its linearization, the tangent line, is still going to be approximately true that the change in y will be the slope times the change in x. We just need to evaluate the slope at our particular location in order to use this. So this is exactly true because we're talking about infinitesimally tiny changes in input and the corresponding changes in output. This is approximately true, so we call this the differential approximation. It's a nice way of putting the derivative to work, right? Figuring out what is the derivative telling you. Well, the derivative is the slope. Slope times change in input should give you change in output, because if the slope is the rise over the run, then the rise should be equal to the slope times the run. If the slope's changing, so it's not exactly a straight line, then this will be approximately true. Okay, another thing we could use the slope for is actually find the equation of the tangent line. We already figured out that the slope of this function near 5 would be the derivative evaluated at x equals 5, and the derivative was 3x squared minus 2, so we need to evaluate that when x equals 5. So we plug in 5. 5 squared is 25, 3 times 25 is 75, take away 2 is 73, so we've got our slope. So we know the slope of our line. We also know that in this original function, if x equals 5, y is going to be 5 cubed minus 2 times 5. 5 cubed is 125, minus 10 gives you 115. So we have the slope is 73. We also know that the graph goes through this point, 5, 115, and that's enough to figure out the linearization. Remember, the change in y is the slope times the change in x. That's exactly true if we're talking about the linear function, the line that approximates this graph. The change in y would be how much does y move away from 115. That's the slope is 73, and the change in x would be how far do we move away from the original x value, right, which is 5. So there's the equation of the line. Now we could smooth this out a little bit. By multiplying out, we have 73x. 5 times 7 is 35, so 5 times 70 would be 350, plus another 15 would be 365, so minus 365, plus we were bringing that 115 over here. So y is equal to 73x. Let's see, if we add 15 to that, we've only got minus 350. Add another 100, we got minus 250. So there's our function. Because it's so easy to graph using software, we ought to graph this function. Let me pull that up here. If we graph this function, remember our original function was this nonlinear thing. Y equals x cubed minus 2x. There it is. And so that's its graph. And then we just figured out that the linearization was 73x minus 250. So we can graph y equals 73x minus 250. You can see we've found the linearization, or the linear function, that approximates the function near the point 5. So that can be very useful as well, as we're taking a nonlinear function and we get an approximation that, as long as we're near 5, works pretty well. So if we zoom in on this function, you can see that there's very little difference between the nonlinear function and the linear one. This is sort of a critical observation. If the changes are tiny, you can pretty much use the line in place of the function. So we have this linearization, or tangent line, can be a nice simplification or approximation for the function. Okay, so when we're using the differential, we're taking the slope times the change in input. We're just pretending like the function is a line, and we're just using that slope that we get from our derivative.